Okay, guys, real quick, I'm just going to go over the basics of how to set up all of these next set of problems. What we're going to be doing with the lab and with these problems is something called satellite motion. It's still circular motion, but all of our pictures are typically going to look like this. You're going to have one big object in the middle, and you're going to have a smaller object on the outside, and the smaller object is going to go around the bigger object in a circle. Okay, so basically, what's going on is this could be the sun and that could be the Earth. That's a type of satellite motion. Technically, anything that orbits is called a satellite. So the Earth would be a satellite of the sun. This could be the Earth, that could be the moon. This could be the Earth, that could be the International Space Station. This could be the Earth, that could be any other satellite that you want to be interested in. And we can put them in all sorts of different places. So ultimately, this is the general setup of everything that we're doing. So, what force or forces are acting on this thing to keep it going around in an orbit? Well, that would be the gravity of the planet. So, force of gravity from the planet or from the sun, if this is the Earth, whatever, is what's holding this thing going around and around and around. Now, normally when we have used force of gravity here, we have used mass times 9.8. But now we're talking about stuff that's like way up in space. And the acceleration due to gravity of the sun at different points in space is going to not be 9.8 everywhere. It doesn't work that way. Okay, 9.8 is only for on the planet. Once you start going up into space, it's not 9.8 anymore. So now we need something new. That something new is an equation that looks like this. Force of gravity equals the big G, say M1, M2, all over R squared. That's called the Newton's law of universal gravitation. Here's what you need to know about it. This equation will tell me the gravitational pull of any two objects. Any two objects. Here's what we have. Here's what we know. Big G is what's called a constant of nature. I'm not going to get into how they figured it out in this video. But all you need to know is it's on your equation sheet, FYI, and will be on any test or quiz that we ever take. It's a really tiny number, 6.67 times 10 to the negative 11th. You don't need to know these units, but it's Newton meters squared per kilogram squared, okay? So that number, anytime you have any equation where that's a thing, it's just this. It's just that 6.67 times 10 to the negative 11th. The mass, M1 and M2, are the masses of the two objects. So again, it might be the mass of the sun and the mass of the Earth, the mass of the Earth, the mass of the moon, whatever, okay? So the mass of the two things, and then the R is the distance between them from center to center, okay? We use R for the distance because when we're talking about satellite motion, it happens to be the radius of the circle, okay? So that's why we use R, the radius of the circle, okay? And that one gets squared. So those are what all those variables are for. All right, so now when we're setting up problems for this circular motion, you might notice if you look at your equation sheet, there's three equations that are on the bottom left of that equation sheet, which say for satellites only. Do not use them for a roller coaster. Don't use them for a car going around a turn. Why? Because I'm going to show you where they come from really quickly, and then you'll see like, oh, it's only for this type of setup. So, all right, if I'm trying to figure out some bit of information about this thing going around, let's say this is the Earth, whatever. So here's the satellite, here's the Earth. I want to figure out how fast it's going to go around. Well, this is where we say, okay, our forces bit, what's the centripetal force? That's force of gravity. So I'd say, okay, force of gravity is my centripetal force. Well, now again, for force of gravity, we can't use mass times 9.8 because if this is some satellite going around the Earth or the moon or whatever, it's not 9.8. We can't use that. We don't know what that little g acceleration is. So what we use for force of gravity instead is this new equation where it's big G. So let's say this is the Earth and this is the moon. I can't remember if I said it was Earth and moon or Earth and satellite. Let's say it's Earth and moon. Okay, so mass, I'll say this is E for Earth. The other m is mass of the moon because those are the two objects, all divided by the distance between them squared. That's going to equal one of my centripetal force equations. We had ma, we had mv squared over r, we had the m4 pi squared r over t squared. Which one we plug in here depends on what we would be trying to find. If we're trying to find time, we'd use the third one with time. If I'm trying to find velocity, which is what I said I would do, I'll use the second one, which has velocity, which would be mv squared over r. And here's the only, not even a tricky bit because I kind of did the math for you on your equation sheet, but which mass is this? When we talked about centripetal force stuff, we were always, what's the mass of the car, the thing going around the turn? What's the mass of the little rubber stopper or the little rubber ball that went around your head during the lab? This is always the mass of the thing that's going around. So this is the mass of the moon in this particular situation. Okay, so this is always the mass of the thing that goes around. From here, our equation is set up. We just say gravity is centripetal force, so we can set these two things up. And from there, we just have to do a little bit of algebra. Okay, notice I've never done this for, hey, a car goes around a turn. Because a car goes around a turn, that friction is what holds a car going around a turn. Not this. I don't need the mass of the car and the mass of the earth. That's not how that works. So that's why the equation that we get to, which is going to be one of those three on the bottom left, you only use for satellites, because this is the setup for satellite motion. All right, so mass of the moon is on both sides. They actually cancel. Whenever you're talking about satellite motion, you don't need the mass of the thing going around. You need the mass of just the thing in the middle. That's it. Whatever the middle thing is, that's what's important. So any satellite that we put in space, I don't care how massive it is. I don't care if it's really heavy or not very heavy at all. It's going to behave the same because we don't care about the mass of the satellite. All right, from there, I actually have r squared and r. If I multiply both sides by r, it makes my squared go away and cancels that one. So what I'm left with is big G, mass of the middle object, which in this case is the Earth, divided by r, equals just v squared, because that's the only thing that's left. So if I want to get rid of that, you can see I just got v squared over here on that side. I'll erase the mass of the moon, because that was canceled as well. So if I want to just get v by itself, I just have to do the square root, and I get v all by itself. Okay, so that was the algebra for this. And you'll find this equation is on your equation sheet. And it says use it for satellites only. All right, but this is the setup where you say force of gravity is centripetal force. I say if you wanted to start this from scratch and not use one of those equations on your equation sheet, that would be the setup where I'd say the big G, mass of the Earth, mass of the moon, all over the radius between them squared, equals your centripetal force, pick equation. We pick mv squared over r, mass of the moon, v squared over r. That's always going to be your starting point. Okay, that's always a starting point on all of these satellite motion problems. You never have to think to yourself, what's holding this thing in orbit? It's always gravity. Always, 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 always. Okay, so you just need to make sure you know the mass of the thing in the middle, and then figure out, hey, what is it that I'm trying to solve? Sometimes you might be having a problem where you actually can solve for the thing in the middle. They've been able to have a pretty good idea of what the mass of different planets are by taking a look at the moons and seeing how far away they are, how long it takes to go around. That's how, like, if you're ever wondering, how do we figure out the mass of the Earth? Doing this. They said, hey, we know how long it takes the moon to go around. We know how far away the moon is. So in an equation like this, instead of solving for velocity, they solve for the mass. So that's one of the ways that you can figure out how massive the Earth is, how massive Jupiter is, how massive whatever, okay? How massive the sun is. So if you're wondering, how do we ever figure out, like if you look at a book, the mass of the sun, how do you measure something like that? Doing this kind of stuff, okay? You don't need to know, if you know about us, where we are, how long it takes us to go around, 365 days, you'd be able to solve for the mass. If I wanted to do that, I would just use my time equation. So I'd say m4 pi squared r over t squared. This again, if I said, hey, I'm switching up my objects, again, the setup is the same. Instead of Earth and Moon, we'll say Sun and Earth. So here's the sun, here's the Earth. This would be the Earth because that's the thing going around. Earth cancels, it always does. And now if I said, hey, I want to solve for the mass of the sun, I would have to multiply the r squared over, divide by the g. Again, we can measure how far away we are with telescopes times 365 days. Big G is this number. We'd be able to solve for the mass of the sun. The setup is always the same. So depending on what we have, we can solve for any of the other things. And that's how we do stuff like solve for mass of the sun. All right, I hope that helps. The lab is very similar to this. You are literally setting up your own solar system. So you would set the object in the middle, the sun or whatever. You'd set up the object on the outside, it'd be a planet, or if this is a planet, that would be a moon. Whatever it is, you're going to be setting that up and you're going to be just playing with it a little bit to see how force of gravity is the thing that holds all this stuff together. Hopefully that helped. Sorry for being so long. Enjoy your snow day, and I'll talk to you guys all next week when we're in class. Bye, everybody.